All right, welcome to my office hours for Monday, June 1st. I'm going to switch over to the math canvas here in just a second. Still no one joining us, but hopefully that will change in a matter of minutes. So I wanted to do an example or two from the first unit to highlight some of the topics that are a little more challenging than the others. And we're kind of in the second half of the first unit now. And toward the end of the first unit, inequalities are one of the topics that I want to make sure that we get some screen time for. So here's an example from objective number 56, which is solving a linear inequality. This particular linear inequality has variables on both sides of the inequality, and it also has fractions, two of the features that make this the perfect kind of example to look at the techniques that you're likely to use, not just in this context, but in some other contexts as well. So let's take a look at what it's going to take to solve this particular linear inequality for W. So anytime the word solve appears in a problem, the objective is to get the variable by itself. So in this example, the variable is W. We need to get W all alone by itself on one side of the equation. So here's an idea. First thing I want to do is I want to ditch the fractions. Anytime you can ditch the fractions, it's a good idea, right? Because even I, as a mathematician, would prefer to do arithmetic with whole numbers rather than fractions if I can get away with it. So we're just going to do one step at the beginning of the problem to totally nuke the fractions, called clearing denominators. And then once that's done, then we'll be able to unwrap the variable. In other words, get all the arithmetic that surrounds W out from around the W to get the W by itself. At that point, we'll have a solution in the form of an inequality. Then we'll be able to write that solution using a number line and using an interval notation. So one step at a time. First, let's talk about clearing denominators, nuking the fractions so that we can work with just whole numbers in the end. Well, the only denominator, the only fraction in this equation is that -3/2 out in the front. So if we're going to clear that away, we need to clear away that denominator of 2. The idea behind clearing denominators is to multiply by a whole number that will clear all the denominators of all the fractions away. And since 2 is the only denominator here, let's just multiply everything by 2. If I multiply everything by 2, distributing the multiplication over the addition and subtraction, then what's going to happen is that -3/2 times 2 is going to become -3 in the beginning, and that was the only fraction that we had. And after our denominators have been cleared, again, distributing that multiplication, we get the new inequality, -3W minus 4 is less than -18W plus 12. So our clearing denominator step is all finished. Now we just need to get that W by itself. And getting W by itself requires a two-step process. The first step of the process is to get all the W's onto one side of the inequality. We can't do anything until we get the W's in one place. And anytime you need to move variables from one side of an equation or an inequality to the other, subtraction is the way to do it, subtraction or addition. It's very common that students will try to divide or something in a case like this, and that just isn't going to do it because the variable here is in a term, an additive term. So to move it from one side to the other, we really do need to subtract. So I'm going to focus in on that -18W on the right-hand side. Subtract that term. Subtract -18W from the right side from the left side. That's going to have the effect of getting rid of the W term on the right-hand side of the equation and then combining with the like term -3W on the left-hand side of the inequality. Keeping in mind that subtracting a -18W is the same as adding a positive 18W. What we're going to get on the right-hand side is just plain 12. We don't have any more variables on the right-hand side, which was the point. And on the left-hand side, we'll combine those like terms. -3W plus 18W will give me 15W, and we still have the -4. So now our W only lives on one side of the inequality, which means now we can unwrap it using the reverse order of operations that I call SADMEP. Let's deal with all the addition and subtraction first. If we can do any addition or subtraction to get the W to be more unwrapped, let's do that first. Then we'll do any division or multiplication we need to do to get the W unwrapped. And then if there are any exponentials or there are any parentheses, that we can worry about those at the end. So according to SADMEP, the first thing I want to do here is see if there's any addition or subtraction that can make my life easier. And there is. If I add 4 to both sides of this inequality, I'll get 15W on the left and 12 plus 4, 16 on the right. Now there's no more addition or subtraction I can do to make this simpler. So I'll go for division or multiplication. In this case, dividing will turn 15W back into just plain W, which is what we want, by dividing by 15. If I do that on both sides of my inequality, I'll get W by itself to be less than 16 over 15. So now the W has been completely unwrapped. And this is more or less a solution to this inequality. Now, the question didn't ask us to do this, but I might on an exam, or a different question might ask you to do this. Let's visualize this inequality, not just as an inequality as it's written here, but also let's depict it on the number line, and let's write it in interval notation. So first of all, for the number line, I'm just going to draw out a blank number line, label maybe a few of the integers here in the middle. 16 over 15 happens to be just a little bit more than 1, so I'm going to label that right there on the number line. And because our inequality has a solution which says that we want the w's that are less than 16 over 15, that means I want that piece of the number line which lies to the left of 16 over 15. So I'm going to shade that, starting from 16/15 and going all the way to the left, quote unquote. In this case, all the way down to negative infinity, if you like. Also, because w is strictly less than 16 over 15 and is not equal to, in other words, because we have the strict form of the inequality sitting right here, and it's not less than or equal to, it's just less than, I'm going to put an open circle right there at 16 over 15 to denote that we're not including that number specifically, but we're including every number which is less than that. So there's a depiction on the number line of what the solution looks like. To write interval notation for it, we need to know 4 things. First of all, what are the lower limit and the upper limit of this interval? Since this interval goes all the way to the left, it doesn't have a lower bound, we're going to say that the lower limit is negative infinity. That's just the way that we communicate that there is no lower extent to the interval which solves this inequality. On the other hand, the upper limit is pretty clear from where we sketched on the number line. 16 over 15 is the upper limit, the upper bound, if you like, of the interval which solves this inequality. So those are the first 2 pieces of information we need for our interval notation. The second 2 pieces are to communicate whether or not these limits are actually a part of the solution or not. In the case of negative infinity, certainly infinities are never going to be a part of our solution. 16 over 15, on the other hand, as we've said, should not be included in our solution because the inequality itself is a less than and not an equal to inequality. In other words, if I try to put 16 over 15 in here for w, I'm going to get something which is false. 16/15 is less than 16/15. So I don't want to include 16 over 15 in my solution. In other words, neither this lower limit, because it's infinity, and infinity is never included, nor this upper limit, which is 16 over 15, which is not included because of the strictness of the inequality, should be a part of our final answer. We'll convey that in interval notation by writing the lower and upper limit with a comma in between, and using a round parenthesis for each limit that we don't include. Negative infinity, which always gets a round parenthesis because we never include it, and in this example, 16/15 gets a round parenthesis also because we don't include it. So this is a complete solution for how to solve a linear inequality, which in this example has variables on both sides of the inequality and also has fractions. We started by clearing denominators. Always a good decision when you start a problem that has fractions, especially if there are multiple fractions. Here there was just a single one. And so it just took multiplying by that fraction's denominator, too, to clear out all the fractions and give us nice whole numbers to work with. Then we had to contend with the fact that there were variables on both sides. So we subtracted the term from the right-hand side, negative 18w, that had the variable, over to the left-hand side. In other words, we added 18w, so that now there was just a single term that had a w in it, and it was on the left side of our inequality. Then we just had to unwrap that variable using the reverse order of operations, first adding 4 to both sides, and then dividing by 15 on both sides. That gives us a solution to this inequality in inequality form. W is less than 16 over 15. Finally, we visualize this solution on a number line by drawing out the bound, 16 over 15, slightly bigger than 1, and shading the entire portion of the number line, which is to the left of that upper bound. We can then turn that into interval notation by identifying the lower and the upper limits of our solution, and then deciding for each of those limits whether or not that limit should be a part of the answer or not. In this example, the answer was not on both cases, and so the interval that we answer with has round parentheses on both sides. Oops. So that was the first example for today, solving a linear inequality, and it had kind of a little bit of everything in it. We're going to do a few more examples in office hours today that involve some of those same techniques showing up in different contexts. One of the things that you'll notice about algebra is that once you get the hang of a few sort of basic techniques, clearing denominators as an example, moving variable terms from one side of an equation to the other is another example, that it's just kind of iterations of those few basic techniques can actually help you to solve a lot of different types of problems in different contexts. And so the expertise, the practice that you get into is figuring out not just sort of, when to implement what technique, but sort of just having the confidence to take a risk and try a technique and see if it works, see if it gets you closer to a solution. And if it doesn't, then try something else. And after enough of that kind of practice, you're going to get good at solving a lot of different types of problems. So I want to move forward and do another example because there's some other examples kind of in the second half of Unit 2 that I feel like could use some additional practice. So let's take a quick look back into the notebook. Yes, okay. So the next example I want to talk about is also an inequality example, except that this particular inequality example also involves an absolute value. Solving equations and inequalities with absolute values in them, in my experience with this course, has been something that causes quite a bit of difficulty for students. And fortunately, the resolution to those difficulties is pretty straightforward. So I'm hoping to give you a flavor of how that works. Here we want to solve the absolute value inequality that says the absolute value of u minus 2 is greater than 3. The question is also asking us to graph the solution on the number line. You notice that this is objective number 61. It's actually the very last objective in unit number 1. So if you make it to this objective before the objective is all due, then you're in really good shape. So let's talk about how to solve this particular inequality by looking at a strategy. And the strategy for solving any inequality which is more complicated than the one that we just did a minute ago, the strategy that I like, anytime you're not sure how to proceed, is to forget for the moment that it's an inequality at all. Make it an equality. In other words, put an equal sign there. And our strategy is going to be to use that equality to cut up and test intervals on the number line to see which ones of them are part of the solution and which ones are not. So here's what that's going to look like. First, we're going to solve the equality, the equation, absolute value of u minus 2 is equal to 3. How are we going to do that? Well, here's the trick that people forget about absolute values. We can make an absolute value in an equation go away, as long as when it goes away, it leaves behind two different things, a plus and a minus, a positive solution and a negative solution. So when an absolute value goes away, it leaves a plus or minus on the other side and gives us really two equations to solve. After we've solved that equation, that's going to define several intervals along the number line. It's going to cut our number line into pieces. It's then going to be our job to test each of those pieces, test each interval that this equality defines on the number line. And by testing, what I mean is we're going to look at the original inequality and see if those intervals solve the original inequality. And then just like in our previous example, we'll visualize our solution on the number line and we'll write out some interval notation for the solution at the end of the day. So first things first, let's forget that this is an inequality for a minute and replace that greater than sign with an equal to sign. So now I need to unwrap the u. I need to get the u by itself. And the outermost thing that's happening on this equation to the u is that absolute value. So let's get rid of that absolute value. And the way to do that is to split it into two pieces. One piece where we take a positive solution, the other piece where we take a negative solution. In this example, what that looks like is we're going to have u minus 2 on the left-hand side. But on the right-hand side, one of our equations is going to have a positive 3. The other is going to have a negative 3. So now I have two equations to solve. 2 is more than 1, so this is a little bit more complicated than it was, but our absolute value is gone, and so that should be good news. And solving each of these pieces just requires a single step, namely adding 2 to both sides. After having done that, we get two values of u, which solve the equality in this example. U equals 5 and u equals negative 1. So that was the first step. Forgetting for the moment that we started with an inequality, we solved the equation and got these two solutions. I'm going to sketch those right here on the number line and put a little equal sign on top of each of them to remind myself that it's at those 2 points that the absolute value of u minus 2 is actually equal to 3. Just a quick note about what this means. So one way to interpret an absolute value. One way to interpret what an absolute value means is to see it as a distance. So if I have the absolute value of something minus something else is equal to 3, what that really means is it's saying that the distance on the number line between two quantities is equal to 3. What are those two quantities in this example? They're u and 2. So one way to interpret the equation that we just solved is we were looking for those numbers that have the property that the distance between that number and 2 is equal to 3. So what numbers are 3 units away from 2 on the number line? And you'll notice that if 2 is right here on the number line, then if I go 3 units to the right, I'm going to find one of my solutions, 5. And if I go 3 units to the left, I'm going to find my other solution, -1. So this helps us to kind of understand what an absolute value is doing in the context of this equation. Okay, so we know where equals is the case. What that does for us is it cuts up the number line into 3 pieces, 3 intervals. And our job now is going to be to test each one of those 3 intervals to see if numbers which lie in that interval solve this inequality or not. So I'm going to label my intervals from left to right. I'll call them A, B, and C. So A is the interval from -infinity up to -1, B is the interval from -1 to 5, and C is the interval from 5 up to +infinity. And the name of the game is going to be to go into each one of those intervals and pick a number, any number at all. So as convenient as you want it to be, as long as it's in the interval that you're testing, and plug it back into the original inequality that we were trying to solve. If it satisfies the original inequality, if it makes a true statement, then we're going to include that entire interval as part of our solution. If it doesn't, then we're going to exclude that entire interval from our solution. So I'm just going to make a quick little chart here of the 3 intervals that we're going to test, the values that we choose inside of those intervals, the test itself, and then the sort of answer. Are we going to include that as part of our answer or not? So for the first interval, interval A on the left, let's choose a convenient representative of that interval, -2, for example. I can choose, again, any number that I want to that's a part of that interval, so I'm just going to choose one that's going to make my arithmetic as simple as possible. U equals -2 is probably as good as we can do here. So I'm going to plug that value, -2, into the original inequality. Absolute value of -2 minus 2, is it greater than 3? Well, using the order of operations, let's evaluate -2 minus 2, -4. Take the absolute value on the left-hand side, absolute value of -4 being 4, and then ask, is this a true statement? Is 4 greater than 3? And the answer is yes. So when we chose a number which was in interval A and plugged it into the original inequality, we got a true statement. And because of the way that we're approaching this problem, that means that not only does -2 solve this inequality, so does every other number that's a part of that interval solve this inequality. So our answer, our solution to this inequality is going to include the entire interval of numbers from -infinity up to -1. So we want to include piece A. What about piece B? Let's choose a convenient number inside of the interval from -1 to 5. Let's choose 0. 0 is always a nice one to work with if you can get away with it. If we plug 0 into this inequality, we'll get the absolute value of 0 minus 2 on the left-hand side, which is the absolute value of -2, which is 2. And is 2 greater than 3? No, it's not. So piece B we don't want to include as part of our solution. Again, if any number inside this interval does not satisfy the inequality, then no number inside that interval will satisfy the inequality. So because 0 doesn't work, neither does any other number between -1 and 5. And finally, for piece C, let's choose a number, I don't know, how about u equals 8? If I plug that number into my original inequality, I'll get on the left-hand side the absolute value of 8 minus 2, which is the absolute value of 6, which is 6. And is 6 greater than 3? Why, yes, it is. So sort of tidy up here. We tested all 3 of the intervals, which may or may not be part of the solution to this inequality. And we found out that interval A and interval C both are part of the solution, while interval B is not. So we have now kind of a visualization of the solution of this inequality on our number line. Let's see if we can make it a little bit more precise. Looking again at the original inequality, we have a symbol here, actually that should say greater than, not less than. Let me fix that. So in the original inequality, we have absolute value of u minus 2 is greater, but not equal to 3. What does that mean for us? It means that we shouldn't include the points at -1 and at 5, because those were the points at which the absolute value was equal to 3. So again, we're going to put open circles there instead of closed circles to indicate we're not including -1, we're not including 5, because at those values of u, we end up with an equal sign and not a greater than sign. All right, so how do we translate this all into interval notation? The degree of difficulty here is that we actually have two intervals that are part of our solution to this inequality. So we need a way of taking both of those intervals and including them both as part of our solution using this notation. Well, one piece at a time. Let's talk about piece A. Looking at the lower and the upper limits of this interval, A has no lower limit at all. It goes all the way to -infinity, if you like. And its upper limit is -1. So in interval notation, we'll have -infinity comma -1. And then we just need to decide, are we including -infinity or are we including -1? Before we do that, let's talk about interval C. Interval C has no upper limit. It goes all the way to +infinity. Its lower limit, on the other hand, is 5. Now let's go through and decide whether or not each of those limits is a part of our solution or not. Do we want to include it in our interval notation or not? Well, -infinity, for starters, because it's an infinite quantity, it's not a number, we can never include it in our solution. So, round parenthesis. Infinities always get round parentheses in our class. How about -1? Well, we decided, again, because the inequality is greater than but not equal to, that we don't want to include -1 either, because that makes u minus 2 absolute value equal to 3. So we'll put a round parenthesis at -1 as well. For the same reason, we get a round parenthesis at 5, and we also get a round parenthesis at +infinity. So now we've written interval notation for each of our two pieces. The last thing we need is to glue those two pieces together to make them a single set that solves this inequality. And all we need to do is put in one more symbol, a little u. This u stands for a union. And what it means is that our solution includes both of the intervals that are listed here. And so in interval notation, the final answer for this problem is the open interval from -infinity to -1 union the open interval from 5 to infinity. So this was an inequality problem that also had a lot going on. We had the absolute value to contend with, and then we also had to contend with the fact that we ended up with multiple intervals in our solution. It also illustrated a slightly different technique for solving an inequality compared to the last example. And in this technique, we replaced the inequality with an equality. We just made it an equal sign, solved the equation, and then used the solutions of the equation to cut up the number line, and then picked a number inside each of the intervals that it cut it up into to test in the original inequality. By testing each of the intervals in the original inequality, we figured out which ones we needed to include in the solution and which ones of them we need to throw away. The great thing about this technique is this technique will work no matter what kind of inequality you're trying to solve. We're not going to do much of it in our course, but when you move forward into pre-calculus next semester, you're also going to solve inequalities with, for example, quadratic expressions on one side, or maybe rational expressions on one side. And as soon as things get more complicated than just basic linear, this is the technique, invariably, that you're going to end up reaching for. Forget that it's an inequality at all, put an equal sign in there, and then solve. Solve the equality, cut up the number line, and then test the intervals on the number line. All right, so we've done a couple of examples of inequalities that illustrate a lot of the common challenges that show up in solving these types of problems that end up at the end of Unit 2. Unless I get questions that want me to look at something else in particular in Unit 2, what I'd like to do is do a couple more examples that involve not inequalities, but maybe some things that can happen in just plain solving linear equations that are, let's say, on the unusual side of things. So I wanted to look at one common bit of confusion, which is what happens when your variables disappear in solving a linear equation. So you got x's, you do something in the equation, all your x's vanish. What are we to make of that situation? And I didn't want to let Unit 1 sort of end before we also have an example of a story problem to look at, and maybe talk about some techniques that we can use, problem-solving techniques that we can use to approach a story problem. So I want to look at two more examples. The first is what happens when your variables all vanish. And the second example is let's look at a story problem and see if we can kind of take it apart bit by bit. So when your variables all vanish, it means that the number of solutions that the equation has is not usual. Most equations, most linear equations, let's say, have the property that they have only a single solution. And by solving for the variable, by unwrapping the variable, you discover what that solution is. But it's not always the case. It's 99.99% of the time the case. But there are cases where you have linear equations that don't just have one solution, that they might have no solution at all, or better yet, they might have all real numbers as solutions. So let's take a look at what to expect when that happens. So again, most of the time, this doesn't happen. Most of the time, linear equations have a single solution, one and only one solution. And so the difficult thing is when the variable disappears. When you suddenly find yourself with no x's or no w's or whatever as part of your equation, it's difficult to know how to interpret that the first time it happens. So let's take a look at how to interpret that. If the variable in an equation disappears, what happens is that that variable's value loses the ability to affect whether the equation is true or false. Therefore, when the variable disappears, it means that the original equation is either always true, in other words, always balanced regardless of what value that variable had, or it's always false, in other words, always imbalanced regardless of what value the variable originally had. So we're going to end up with an equation which was either always true from the beginning or which was never true from the beginning. So our strategy is not going to be any different. We're not going to be able to tell ahead of time that this is going to happen. So we're going to approach solving this linear equation the way that we usually do. Both of our examples here have variables on both sides, so we have to contend with that first. Let's think about getting all the variables onto one side of the equation, always by subtracting. Once the variables are all on one side, we'll be able to reverse the order of operations to unwrap the arithmetic that surrounds it and get the variable by itself. And then, if the variable happens to have disappeared, you're going to be left with an equation that has only numbers in it. If that equation is actually balanced, if it's true, it means that all real numbers must have been solutions to the original equation. If the equation that you get there is false, if it's imbalanced, that means that the original equation is also fundamentally imbalanced and that there is no value of the variable which solves the original equation. So when your variable disappears, you either have a situation where there is no solution to the equation or a solution where every possible value for the variable is a solution. Let's look at what happens in part A. Let's solve this equation, again, by first of all thinking about getting all variables to one side. But before we even do that, let's simplify. We've got an expression on the left-hand side that has some parentheses in it. I've got an expression on the right-hand side that has some parentheses in it. So before we do anything else, let's deal with that. Let's get around the order of operations here by distributing the multiplication outside those parentheses across the addition and subtraction that's on the inside. If I do that, then on my left-hand side, I'll get 3w minus 6 when I distribute. On the right-hand side, negative 2w minus 6. Then to finish simplifying, I've got a pair of like terms, 3w and minus 5w on the left-hand side, which when I combine by subtracting those coefficients, 3 minus 5, I'll get negative 2w. So after all the simplifying happens on the left and right-hand side of this equation, I get an equation which says negative 2w minus 6 is equal to negative 2w minus 6. And already, if you're looking at this equation, your sort of antenna is going up and saying, well, this is weird. I have an expression on the left-hand side, an expression on the right-hand side, which are now quite obviously identical to one another. So what's going to happen? Well, rather than worrying about that, let's just go back to our strategy. Let's get all variables to one side of this equation. Again, always by subtracting. So I'm going to maybe focus on that negative 2w that's on the right-hand side of this equation and try moving it to the left by subtracting negative 2w. That's the same, of course, as adding positive 2w. And when I do it, not only do my w's from the right-hand side go away, negative 2w plus 2w is going to give me 0w, otherwise known as 0. But the same thing happens on the left-hand side also. Negative 2w plus 2w is 0. And when the dust settles, the only things left on the left and right-hand side of this equation are constants. Negative 6 is equal to negative 6. So my w's are gone. They have vanished. And therefore, again, w has lost the ability to affect whether this equation is true or false. Which means that because this equation here at the bottom is completely independent of the value of w, that means that the equation in the beginning, because it's equivalent to it, must also be completely independent of the value of w. It's either always true or it's always false. And looking at the equation at the bottom here, negative 6 equals negative 6, because it's always true, it's obvious that minus 6 is equal to minus 6 now. That must mean that our original equation must also always be true, regardless what value w takes. So all real values of w satisfy the original equation, because all real values of w satisfy this identity that we derived at the end. Identity, by the way, is the name that we give to this phenomenon, right? That we started with an equation that had variables in it, but whose truth value was always true regardless of the value that that variable took. So how do we respond to this question? We're going to choose the option that says all real numbers are solutions. So here was an example where the variable disappeared, and when the variable disappeared, we were left with something which is always true. In this example, negative 6 equals negative 6, always true. Therefore, since that equation is always true, the original equation is always true as well, and all real numbers are solutions. Let's see what happens in part B. Same strategy, maybe a different result, we'll see. So in this equation, we want to get the v by itself. And again, because we had some simplifying to do on both sides, let's distribute the multiplication across the addition and the subtraction. I'm going to get 10 minus 5v minus v on the left-hand side, 2v plus 2 on the right. Combining the like terms on the left, negative 5v minus v is going to give me a negative 6v. So I'll get 10 minus 6v is equal to 2v plus 2. Now all my simplifying is done. Let's get all my variables to one side. Again, always by subtracting. If I subtract 2v from both sides, I'll end up with just 2 on the right. And on the left, when I combine the negative 6v and the minus 2v that I got here, I'll end up with negative 8v. So I'll have 10 minus 8v is equal to 2. Now I have the variables only on one side, and so I can unwrap that v by reversing the order of operations. Addition and subtraction first, so subtracting 10 from both sides will give me negative 8v is equal to negative 8. And then division and multiplication. Dividing by negative 8 will get the v by itself and give me v is equal to negative 8 divided by negative 8. V is equal to 1. So notice what didn't happen in this example is that the v's didn't all disappear. Right? Unlike the example in part A, we did all of our reverse order of operations and the variable v survived that process. Right? We could always find v somewhere in our equation, all the way up until the end when v is sitting by itself. That means that this particular equation has a single solution. There's a single real number which makes this equation balance, namely the real number 1. And so this is an example of a linear equation with what we call a unique solution. There's only a single number, namely 1, which balances both sides of this equation. So two very different things happened in part A versus part B. We used the same strategy to solve each of these equations, but the results were very different because in part A, our variables disappeared. They went away, they vanished. Right? And when that happens, that means that the equation that you get either was always true to begin with or could never have been true to begin with. In our example, because the equation that we got, -6 equals -6, is always true. It means also that our original equation was always true to begin with, and all real numbers, W, balance the equation that we started with in part A. It's a very unusual situation. It's very rare that this happens, but when it happens, that's how you can interpret it. Part B is a bit more of a usual conventional problem. Because we didn't have all of our variables disappear, we always could find V at every step of the game. And when we got down to the V being by itself, we got the unique solution. This linear equation, V is equal to 1. So there was an example of something unusual that happens in the process of solving a linear equation. Luckily, as I mentioned, it doesn't happen very often. A mathematician might say that the generic linear equation has a unique solution, right? It's a very rare occurrence for the variable to vanish the way that it did in the last example. So if that's the case, then you can be reasonably certain that when you solve a linear equation, the usual techniques that we talked about will get you to that unique solution, right? And the techniques were move all the variables to one side of the equation. In other words, get all the variables so that they're by themselves so that we can unwrap them using reverse order of operations. And then use a reverse order of operations to get that variable by itself. But what happens if we can't even get to a linear equation in order to do that in the first place? What happens if we start with a story problem? And what are some techniques that we can use to approach the solution of a story problem, especially if that story problem involves some kind of challenging arithmetic objects, for example, fractions. So I want to look at an example from Unit 1 that sets up a story problem in such a way as to, they think that they're going to require you to put together an algebraic equation, a linear equation that involves fractions in order to solve this story problem. But I'm going to actually show you kind of two ways of approaching this. One way that actually has you translate the problem into algebra per se, and then solve an equation using algebra. But we're not going to do it that way in the beginning. For the first approach to it, we're going to look at a way of just sort of talking our way through it, sketching the right picture, and maybe coming up with a method of solution that doesn't involve us using algebra, but only arithmetic, which would certainly be a benefit if we can get away with it. Oops. So for this example, I want to go to objective 50, which is called solving a fractional word problem using a linear equation. And this is the problem that involves Ruben and his gas tank. His gas tank is 2/5 full in the beginning of the problem. Then he goes and he buys 6 gallons of gas, and afterwards his tank is 7/10 full. And the question wants to know how many gallons in total does Ruben's gas tank hold? So we got a couple things going on, right? We got a story problem, which means that all of the arithmetic operations that are going to help us in this problem are buried inside of the context. So it's going to take a little bit of work to take those arithmetic operations out of the context of the verbally stated problem and into a method where we can understand them mathematically. We also have fractions, which of course is everybody's favorite thing. So let's talk strategy first. And because I'm very visually oriented when it comes to understanding mathematics at all levels, really, I like to start by drawing a picture. That's just how I'm wired. And there are a couple different ways to do this. When I first read this problem, I thought let's think about what his gas gauge looks like. And so I'm going to sketch out his gas gauge over here on the left. He starts out at 2/5 full. Let's suppose that the top of the gauge is both empty and full, which would be maybe a little confusing, but I kind of thinking of the gas gauge like a clock here or something. So 2/5 is a little less than a half, so it's maybe down toward the 5 o'clock position on the clock. So that's where his gas starts. Then he buys 6 gallons, so presumably the needle's going to go up. And when it goes up, it's going to go up to the 7/10 level. So this is kind of a depiction of what's happening in this problem. And the question is, how many gallons in total does his tank hold? So if the needle went all the way to full, how many gallons would be in his tank? And so that's what I tried to do when I first drew a picture for this problem. And I realized it might not be the most useful picture for the sake of figuring out the arithmetic that we need in order to bring this problem home. So then I decided to look at it a different way. Let's think about his gas tank instead of his gas gauge. So I'm going to kind of draw his gas tank as this little cylinder here. And in the beginning, his tank starts out 2/5 full. So the gas level is sort of 2/5 of the way, slightly less than half. It's actually 40% of the way from the bottom to the top. So that's where his gas gauge is going to begin in the problem. At the end of the problem, his gas gauge is going to be 7/10 full. And so the level of gas in the tank is going to be 70% of the way up the tank. And the difference between those two levels is supposed to have been the 6 gallons of gas that he bought in the problem. So this is a new diagram that I think is going to be a little more useful to helping us figure out what's going on in this problem. He starts out 2/5 full, then he throws 6 more gallons on top of it and ends up at 7/10. And the question wants to know, how big is the tank? I want to know how big this total tank is. So let's talk about an approach that doesn't use algebra for a moment. And that approach starts, for me, by asking, well, how much of the tank is made up by this 6 gallons that he put in? And the answer to that question is going to ask us to determine the difference between how full his tank was in the beginning, 2/5, and how full his tank was at the end, 7/10. So what I need to know is, what's 7/10 minus 2/5? How much of the tank is that 6 gallons? And so it looks like we have to subtract a couple of fractions, 7/10 minus 2/5. Because both of those fractions, though, have denominators whose factors are only 2s and 5s, 5 and 10, that means that we can write decimals for these instead of fractions. If that makes you more comfortable, it's something you can do, right? And I'm going to encourage you to use decimals anytime the decimals terminate, right? So 5ths, 10ths, 20ths, 25ths, 50ths, 100ths, halves, fourths. Anytime your denominators have only factors of 2s and 5s in them, your decimals will terminate, and then using decimals comes with no loss of accuracy and can be very much easier cognitively to figure out. So I'm going to turn 7/10 into 0.7 and 2/5, which is the same as 4/10, into 0.4. Because it really is simpler to subtract two terminating decimals in their decimal representation instead of doing them with fractions. 0.7 minus 0.4, line them up and subtract a decimal point, is going to give me 0.3. So now I'm able to say that the 6 gallons that Ruben just bought makes up 0.3 of his tank. The question then is, if 6 gallons is 0.3 of the tank, then how much is the tank? Well, it's going to be 6 gallons divided by 0.3. How do we do 6 divided by 0.3? Well, let's just move the decimal point in the denominator to the right one to give me a whole number. But if I do that, I have to move the decimal point in the numerator to the right one also and turn 6 into 60. So 6 divided by 0.3 is the same as 60 divided by 3. And that's a pretty friendly whole number division problem whose solution is 20 gallons. So according to this, Ruben's gas tank holds a total of 20 gallons. Let's talk our way through the problem one more time. This would have meant that Ruben started at 2/5 full. At 2/5 full, he would have had 2/5 of 20. That's 8 gallons in his tank in the beginning. So Ruben started with 8 gallons. Then he goes and he buys 6 more gallons. And so we know now in total, Ruben is going to have 8 plus 6, 14 gallons in his tank. Now, what proportion of 20 is 14? Well, it's 14 over 20. And if I reduce that fraction, 14/20 becomes indeed 7/10. So this would appear to be a correct solution to the story problem that we started with here. And we didn't have to use algebra to get there. We just drew kind of a clever diagram. And there was enough suggestion of arithmetic in that diagram to help us figure out how to reason our way into the size of Ruben's gas tank. Of course, it's a little bit not dishonest. This is a really, really good way to solve this problem, if I do say so myself, but it doesn't use algebra, right? It doesn't help you to get practice with solving linear equations that involve fractions using the techniques that we're learning about algebra. So for the sake of completeness, let's take another look at this problem that does involve us using algebra, probably the way that the authors of this problem originally intended us to do. So using algebra, what we need to do first of all is figure out what's our unknown quantity, what's our variable, what's the thing that we want to solve for. And highlighted in orange on this slide, we can see that what we were solving for in the first place was the size of Ruben's gas tank. So let's make that our variable. Let's call it T, T for tank. So if T is my variable, what do I know? I know that Ruben starts in this problem with a tank that's 2/5 of the way full. So how much gas is there in that purple slice? If the tank holds T gallons and it starts at 2/5 full, then that must mean that Ruben is starting with 2/5 times T gallons of gas. But then Ruben goes and he buys 6 more. And so how many gallons in total does Ruben have at the end of the process? On the one hand, just looking at the diagram, Ruben has the purple gas, 2/5 T, added to the green gas, which is 6. And so in total, he has the sum, 2/5 T plus 6 gallons of gas. And that's one way to look at how much gas Ruben has at the end of the problem. But it doesn't help us to solve for T because we need to look at this amount of gas in another way as well. How do we look at it in another way? We have to remember that we know that at the end of the process, his tank is 7/10 full. So on the other hand, we can look at the amount of gas that he has at the end of this process as 7/10 of a tank. So on the one hand, it was 2/5 T plus 6. On the other hand, the amount of gas he has at the end is 7/10 times T. And the claim is that those two amounts of gas are the same. That's what gives us an equation to solve. Without that equal sign, there's nothing we can do. But once that equal sign is put into the problem, now we have an equation. It happens to have t's on both sides. It happens to have fractions. But we know now, based on the techniques that we've seen sort of today during office hours, how to get the t by itself and solve this equation. So what's our strategy? The first part of the strategy, because we have fractions, should be to get rid of those fractions, nuke them, blow them out of the water by clearing denominators. In this example, we have 2 different denominators to contend with. We have a fifths on the left-hand side. We have a tenths on the right-hand side. So to clear both denominators simultaneously, we can do that by multiplying both sides by any common multiple of 5 and 10. The smallest common multiple we could choose, which happens to be the easiest one to work with, is 10. In other words, if I multiply both left and right-hand sides of this equation by 10, then all of my fractions will be gone. And I'll have only whole numbers to work with, and what a wonderful world that will be. So multiplying by 10 on both sides of this equation, distributing across the addition on the left, will give me 10 times 2/5, that's 20/5. 20/5 is better known as 4, which is a whole number because that's the whole point of this process. And then I'll have 10 times 6, so that'll give me plus 60. And on the right-hand side, 7/10 t times 10 is going to cancel the 10s and leave me with just plain 7t. So now my denominators are cleared. There are no more fractions, but we do have a variable on both sides, a t. So let's tackle that by getting all the variables to one side by subtracting. Subtracting all variable terms to one side. And in this example, I'm going to choose to subtract the 4t. We could have done it the other way, but this way is a little nicer because it's going to give me only a single term on both the left and the right once I'm done. So subtracting 4t from the left is going to leave me with just 60. Subtracting 4t and combining like terms on the right will leave me just 3t. So my equation is 60 is equal to 3t, which I can solve using only one step in the reverse order of operations, dividing by 3 to get that 3 off of the t. And the solution that I get is t equals 20. And wouldn't you know, the solution that we got to this problem doing it the algebraic way hits the nail on the head with what we got doing it without algebra. But this way is somehow a little bit more satisfying because we were able to plug in these algebraic techniques that we've been working on building today in other contexts. So the big takeaways from what we looked at in office hours today are, first of all, any equation or inequality that you want to solve that has fractions on both sides, or even on one side, right? Clearing denominators is going to be your friend. In one fell swoop, it eliminates all the fractions that could otherwise screw up your arithmetic along the way and gives you problems that only have whole numbers in them once you're done. Clearing denominators is going to be the best technique that you forget to use all the time, so don't forget to use it. And the second takeaway is what happens when there are variables on both sides. And the answer is always the same, fortunately. It's add or subtract to move the variable terms from one side of the equation to the other. Because once the variable terms are all on one side of the equation, then reversing the order of operations will unwrap that variable for you and get the solution. So I think we've expired our time in office hours today, but I want to thank any and all of you who have come in to watch today and who've contributed questions offline within the last week. This concludes our office hour sessions for the first unit of the course. So unit number 1 is due on Wednesday, and then you're going to get pushed along to unit 2 once that due date has expired. And any unfinished work from unit 1 is going to get rolled forward. Which is not quite as helpful as it sounds, because my impression is that you don't actually see that rolled over work until much later in the semester. Because once Wednesday hits, you're going to want to start working on Unit 2 right away. You're going to start talking about exponents and polynomials and factoring and all kinds of other fun stuff. And your days of linear equations and expressions and inequalities is going to get left behind for a while. So when we reconvene for office hours again on Thursday at 3 p.m. this week, I'll have a few more examples of how to handle exponents and some of the techniques that you can use to make sense of simplifying expressions with exponents in them to start at the beginning of Unit 2. But between now and Wednesday, your task is to finish up with Unit 1 to the extent that you can. Again, trying to get as much of it as you can get done, and distribute that practice. Make sure you're doing an hour or more each day this week if you can, because that is absolutely the way that you're going to remember and retain this information and actually be able to make more positive progress, as opposed to sitting down and trying to do 6 or 7 hours at a time, which tends to burn you out. So try and break up the work, stay on top of it. You have a progress report due with your teams in Blackboard today, so make sure that you get to that before 5 p.m. this afternoon. And then I will see you again on Thursday at 3 in my office hours.